pleasure to welcome you all on behalf of the Institute of Science and the Indian Academy of Sciences to this lecture, special public lecture given by Professor Ravi-Chandar. The name Ravi-Chandar, and we are particularly happy at the University of Texas at Austin on how things break. From Bangalore University and his diploma in engineering Institute of Technology, and his master's in from the California Institute of Technology in Pasadena. He's widely recognized for his work on fracture and mechanics of materials. He's published more than 150 journal papers on a variety of topics, including instabilities, fragmentation, and dynamic fracture, on which he has also published a book.
Deliver this public lecture. I'm going to try to do this with only two equations through the entire presentation. So it may be boring to those that want to mathematics, and probably more interesting to those that are interested in physics. We'll see how it goes. Professor Jeremy indicated that I got a bachelor's degree from Bangalore University. That's true. I was here in Bangalore for 4 years, last 15 years, at the St. Joseph's College. Lived in Cooktown, and it was the time when things were being sold unbreakable. Of course, they were not breaking in the manner in which you broke a glass bottle of ceramic plate. When I left from here, I got into engineering, breaking fast, and eventually ended up. I was about 10 years old in my laboratory. Turned all the lights off. It was an out band. And the light doing this. And what I'm going to tell you is the story of incidents instigated further in this area. Most sophisticated high pressure gases. Its stream going up and down over in the 1800s. Cover page of Boston Globe 11, I believe. The Boston molasses explosion, molasses, it exploded, and molasses went, I wouldn't say flowing into the streets, but it did, creeping into the streets, and destroyed a lot of facilities, horse-drawn carriages, and unfortunately also killed. Accidents like these happened periodically, and interest in being able to design against them, to learn about why these fractures occurred. This is also a very famous example. This was a T2 tanker that was in a port, sitting still, early in the morning. It was very cold, and all of a sudden, a ship broke into two pieces. The reports at that time said that the age of jet aviation came with a very beautifully designed, beautifully crafted airplane, British de Havilland Comet. After nobody really knew why. One of the forensics to figure out why this fracture occurred. They did was a huge tank, put the entire airplane in there in order to remove gravity loading, and then simulate the flight loads on that to cycle it through to the same number of cycles that the airplanes in flight had, the ones that crashed had gone through, and they found the idea of fatigue cracks in pressurized vessels. Two theories. One where all of it worked the way. This was the Aloha Airline crash in 1988. Due to a complex set of circumstances, a line of rivets started unzipping, a crack had appeared, and that crack then reached a bulkhead, turned around in both bulkheads, and just popped off a little piece of the fuselage. Not a very large loss. There's been a theory that's been built on how things break in such structures. And it's not just engineering structures of the type that I have shown. I'll go through a few other examples. Now let's see if we can in our laboratories. The origin goes back to atomism. Everything's bonded to it, and you have potential that allows the interaction between these to be calculated. And here's the energy picture. The minimum point here is the equilibrium interatomic spacing. You apply a if you apply a tensile force, a pulling force above a certain threshold, solid will break. The atomistics will tell you that. I'm going to define what a crack is, not right now, but in a little bit. Can I ask you to help me a little bit? I forgot to bring a piece of paper. I need a piece of, that would work. Yes. Do you need it? Okay. Not right now, but in a few minutes. So there are different buckets of energy. The energy that you supply, the energy that's stored in the bulk of the solid, and the energy that goes to the surface. That last term is a very tiny amount. For most materials, it's on the order of 1 joule per meter square. But if you ignore that, you ignore surface penalty altogether. So you have to keep that. So Griffith then suggested that you could have an exchange of energy between the elastic energy in the body, or more generally potential energy in the body, and the surface energy of the crack under suitable conditions. And then you give these names. You call the energy from the mechanical part of the system that gets released as the crack, the defect grows, to be the energy release rate, and label that G. The surface energy, let's label as gamma. So then we have a condition for failure, which says that if the elastic energy that is recoverable from the mechanical part of the system, in fact, this becomes, in addition to creating a free surface, you're always adding additional of the new surface that you create. Exactly the surface energy for this. And it turns out that for most materials, this penalty anywhere from 100 joules per meter but the energy release must be able to provide whatever in this case. So I'm going to pull as I can. It can't jump. So it cannot go over that. I didn't apply a fraction of the flight when I pulled on it. Now I have created this. So as I played around with the barrier a little bit, jumped over the barrier. There are many ways in which you can overcome this barrier. The way I did this here was mechanical. I introduced a defect. I could do this chemically. Stress corrosion. What you do is into the vicinity of the defect to attack water. So you bring water into the crack tip vicinity, it attacks the oxygen that's in the SiO2, pops off that bond, and then the bonds are broken. They're in polycrystalline materials. The right one is an aluminum, the left one is a stainless steel, but you have some corroding species that goes into the grain boundaries and starts cracking up. So very low mechanical loading, but sufficient chemical potential from the corroding species, and you can make these cracks grow. But they're extremely slow. This glass will crack at about 10 to the minus 9 meters per second or something like that. What I've shown here is the Apple headquarters or Apple store in New York City made of glass. If the crack's only going to grow at 10 minus 9 meters per second, we're all safe, right? It's not going to go and break this in the lifetime of most of the people in the universe. Fatigue is another way in which you can overcome this barrier. You don't crack everything all at once by robbing the elastic energy from everywhere. You do it piecemeal, in a little place at one location, another place at another location. As you extract energy during the cyclic loading, you could generate fatigue. Already showed you the comet. I'm now going to show another example. Cutting, machining, and other operations, chewing, biting into food, eating chocolate, all of those are fracture operations. I'm going to show two interesting examples. This is cheese slicing. There are different types of cutters. This is very important in the food processing industry to be able to cut things efficiently with low energy consumption. This is a wire cutter. The wire digs a trench and separates these two surfaces. There's a layer of damage to the cheese that's left on the surfaces of what it's cut, but you can calculate how much work is needed in order to make this to go. Most of the body remains unstressed. It's only the vicinity of where the punching of this wire goes in. Think about a cheese slicer that's a knife blade of that kind. In addition to the work that's needed to separate the cheese, you have to pay for the friction on the two sides of the knife when it's touching. That has implications in earthquakes, and I'll talk about that a little bit later. And the last example of cutting is one everybody is familiar with. This is a paper cut on a finger. Very little work has been done on the person's hand, but it's a deep cut that's very easy to make. If you try to tear the same skin by other means, by pulling on it, you're going to spend an enormous amount of work in stretching everything that's outside. Very little work is really needed to make the cut. So in designing efficient cutting operations, you have to think about how you spend the energy that you have. There are applications of this also in anthropology, in archaeology. People go and look at fossils and teeth in particular, and look at the damage in the teeth, and based on that, going backward, to try to find what kind of objects would they have been able to eat. So there's an application of fracture mechanics in those kinds of areas. And the last one is a large number of scientific and engineering applications, and I'm going to go through a few of these. This is the San Andreas Fault in California. Two plates, the Pacific and the Atlantic plates, are meshing against each other, moving in some direction relative to the line of the fault, and therefore they apply both a normal stress, compressive, and a shear stress that is trying to slide it. So in a sense, this is like the cheese cutting problem with sawing motion, right? Then there are a number of theories about how these things occur when an earthquake event occurs. This is a cracking event in that case. The next few I'm just going to scroll through. That's the ice shelf in the Antarctic breaking up. In order to find material properties, people make small specimens out of this ice block. That's on the order of 10 meters to a side, and then do compact tension tests on that in order to find properties of these materials. This is John Dempsey and Clarkson. There are formations, rock formations and things like that that you could see walking around various geological sites. This is one where a crack went straight down but created interesting patterns, and we'll see more examples of that kind. I'm going to skip through that. Engineering failures. These are two pipelines, gas pipeline made out of steel and made out of a polymer. These pipelines could be hundreds of miles long, and when a fracture event of this occurs, it could tear up kilometers at a time, and you'll have to replace them, right? So understanding how these things fail is an important engineering task. It's used in forensics. This is the Lockerbie terrorist incident in Scotland where a Pan Am flight was downed. And there are large numbers of cracks that went longitudinally. The question for a person that wants to design aircraft is, could this aircraft have been hardened in some way that it could have survived that blast incident? For example, just venting the explosion products out here, but then preventing these longitudinal cracks would have maintained structural integrity of the aircraft. Last two examples. The one on the left is teeth. This is the dentin enamel junction, and from there's a lot of cracking that occurs just from the chewing motion. And the one on the right side is from our chairman. It's a microscale specimen with a few microns to a side, doing experiments on cracks on silicon objects that are used in various computer chips and so on. All right. So that's a laundry list of problems that have fracture as an underlying theme in there. And they fall into one or more of these categories. And in order to design against them, all you need to do is calculate the energy that can be released by the elastic system and whether that's sufficient to feed the fracture energy that's needed in order to create that new fracture surface. Much of this framework was developed by Griffith in about 1920 and then finished in about 1924, but it wasn't used because it was very difficult to implement this in practice. In other words, it was difficult to be able to calculate this for arbitrary crack geometries. So it took another 30 to 50 years to fully formalize this theory of fracture. And it took the role of two additional individuals, George Irwin and Max Williams, to bring about the right criteria for practical use. So now I'm going to define a crack and a crack path. I was told by my hosts here that there was a lecture of this kind many years ago given by Professor Valluri, and in the audience was Sir C.V. Raman, and they had a discussion about the definition of a crack. And apparently in the end nobody agreed on what it was, or at least Sir C.V. Raman was not convinced of the definition of a crack. I'm going to define a crack, and we'll see if there's a disagreement, and we'll engage in it. The idea of a crack is that it is a surface, a special surface, across which there is a different set of material properties in comparison to what the properties are in the bulk. That's a starting point. That surface is terminated by a front, and we'll call this the crack front. This object is a crack. This is embedded inside some other large object. So this crack front may meet the boundaries of the object, or this crack front may be completely embedded inside the object itself. So think of a very large sphere and a very small, flat, circular surface inside of it, fully embedded in there, and across which you're able to transmit forces in a different way than you would in the bulk of the solid. So that would be a crack. The front, as you apply forces on the outside, may be able to move and evolve with loading. And this green shaded plane is my imagined evolution of the crack as you apply the load. So the question is, what minimum things do you need in order to define how this surface is going to evolve? I've put in a triad of vectors, unit vectors, T indicating the tangent, N normal to the surface of the crack, and B the other normal. It is not the Frenet triad. The N and the B are switched. But I want the normal to be perpendicular to the surface of the crack at every point. If you now make a cut at some arbitrary location perpendicular to the T direction, you expose what happens in the NB plane, and we think that the crack is going to extend, move, increase in length along the NB plane. So it goes from here to there. So at every point along the crack front, if you prescribe what is the crack extension in the NB plane, you can recreate the crack front in the next step. It's an Eulerian description for a moving boundary. Now you can think of three symmetries. This is the plane of the crack. If the loading is perpendicular to the plane of the crack in the N direction, this will be called a mode 1 or an opening mode. If the forces are in the B direction, this is a shearing mode, where the crack is being sheared parallel to itself, and this will be called in-plane shear. And the last one is when the forces applied are in the T direction. This is called anti-plane shear, or mode 3. And in each one of these, the crack does something different. And if you now look at a local picture, instead of looking at just the global energy balance that I talked about, how these cracks develop. Or let me just make one point here. There's something that goes on in which the material from being damaged here to intact material in Spitzer process. Now we can read the elastic must calculation by what gentlemen did, George Irvin and Max Williams. They calculated for an arbitrary crest state would be near the crack relation. The crest, first of all, was that you can look at will have the same character at near the tip, and in particular that character is that the stresses go as 1 divided by square root of r, which means as r becomes smaller and smaller, the stress will become larger and larger, with an amplitude factor that we'll call k. This is called the stress intensity factor. Irwin also made a connection between this object, stress intensity factor, and the elastic energy. So you get a very simple relation between these two that allows you to calculate the energy that can be extracted from the elastic system without doing a whole lot of calculations. Other people do a lot of calculations. You use them and calculate what this energy release could be. That very simple idea allowed Griffith's fracture criterion to be implemented in practical circumstances by the simple object or process of calculating what the stress intensity factor is. Because now you can postulate the failure criterion, the crack equilibrium criterion, by saying if the stress intensity factor meets this equation, the crack will fail. There's been a very large kind of cottage industry calculating this quantity, the stress intensity factor, for numerous geometrical arrangements and cracks. One example that I've shown here is if you had a plate of some width W and you had a crack of length A loaded with a load P. This is the load P at which failure will occur for this particular geometry. Places like Boeing and other companies have created huge charts of this kind of residual strength diagram that take into account not just the strength of the object, but also the presence of a crack. This theory has been extremely successful in that we have now structures that are built to be fracture critical, that they obey this criterion. The stress intensity will never exceed this equality. And then you're able to operate airplanes, bridges, automobiles, whatever, under fracture critical conditions, not strength critical conditions. Let's move on a little bit. Symmetry that was opening symmetric with respect to the crack. Kind of criterion can be extended. Therefore, the parent crack in this NB plane by adding one more point that says the crack will fish locally opening. Set to 100 degrees Celsius or something like that, and then quenched in. This quench creates a crack. And when I play this, crack tip is here. The glass gets into water, the same distance from the water, and it keeps on growing. So this glass piece is being broken into two. There's a straight line crack, accelerated straight line crack. Then I jumped a little bit farther out from the cold waterfront, and now I'm actually stuck towards the center. And when a brief second, you'll see there. Okay. So back to this criterion. This is adequate. And if you knew what the fracture energy requirements were, you can calculate when the crack would burn more energy by creating more structure to the fracture process itself. The fracture process starts out somewhere sub-micron scale when it initiates, but by the time it's ready to branch, it's on the order of 100 microns in diameter. And that's what leads, when the fracture process becomes so large, there are instabilities that set in that create these events of branching or fragmentation. The calculation of this branching is a little bit involved. The first person to attempt this was Elizabeth Ioffe in 1951. And the idea is very simple. The calculations have morphed in the years since, but the idea is still very simple. If you want to move a crack fast along a line, the material you try to run the crack out, but you create high stresses, not a detail of that calculation, depending on what model you use. Ioffe's calculation showed wave speed. Eshelby had for the structure that's created. Yes, one that I had many years ago, and another one Jay Feinberg did. I had lots of defects in front of the crack, of micro cracks, and they start deviating branches. Feinberg came up with something that's similar to this, will create branching. Very qualitative in the way that we think about it to grow. And for this, back to the one symmetry of the nodes 1 and 2. Think about back as mode load plus a shearing mode load. Criterion of localcy posed for the mode 1 of maximum tension, maximum principal stress. The tilt. But then to that. And you can, a second simulation is for the pressurized semi-infinite crack. Grows initially straight and then bifurcates or branches into multiple branches. And all of this is done without any intervention, remeshing, or anything of that kind. It's just one smooth implementation of the entire energy balance equation. All right. The last one is just for fun. This is a glass plate. It's pressure loaded in the backside of this, and you see how many cracks it creates. It's on the order of 15 branches that it creates from one crack. I've tried to tell a story, maybe jumbled, maybe back and forth, but that's the story of fracture. This is how things fail, and this is what we need to model. So let me stop and see if you have any questions. Thank you.
Thank you, Ravi, for a lovely look at fracture across length and time scales. Yeah.
Yeah. It depends on a few things. The normal to the shear stress on the interface, and it depends on another thing that I didn't say anything about, which is in these things you need to have a model for how slip occurs as a function of rate at which slip occurs. So if you have the slip stress to the slip rate dependence, one way or the other, weakening or strengthening, you would expect such transitions to occur. Yeah.
So in addition to the branching there,
Yeah.
I noticed from the top and the bottom something happening.
Nucleation. And this happens in real materials in the examples. This is actually recreating an experiment we've conducted. So there is a wave that comes from here and it reflects. There are waves from the corners that come around here. Many times they reinforce. And because phase field models are able to nucleate cracks, you see such nucleation.
What are the boundary conditions there?
They're all traction free. Yeah.
The other question is, so since the phase field is emerging as really a powerful
Right.
method, especially in this context of brittle fracture, what are your thoughts on the applicability of this to a ductile metal where you have dissipation and multiple scales? What would it take to make it happen? Like you mentioned this parameter from 0 to 1, the
Right.
order parameter, degrading the elastic, the stored energy. How would you do that
Right.
in a ductile?
So you can change how you degrade your material properties. In addition to, well, degrading elastic behavior is probably adequate. You will stop accumulating plastic strain if you start degrading elastic properties of the material, right? But you have to be very careful. This hasn't been done yet in a satisfactory way. But in principle, there isn't any barrier to this thing. The phase field will just control what happens in the crack surface and a very small fracture process layer. Doesn't change what happens to bulk plasticity. So you do the bulk plasticity the way you normally would, but account for dissipation in addition to the elastic dissipation of the surface energy. You need additional Oro-1 type dissipation for plasticity.
So, excellent lecture. Thanks a lot for the exciting explanations. I was in your talk some 20 years ago at Rice University when you gave the same talk. But since the simulations and
the advances that were made now. I just want to ask you, you showed the Giant's Causeway, the Ireland Giant's Causeway. But I was also of the impression that it's the lava that was formed, and it's nice looking hexagonal cracks.
Thermal cooling crack.
Oh, it's a thermal fluid.
Cooling.
Oh, thermal cooling crack.
Right.
Okay. That's when the lava contracts.
Right.
Okay. And does this have anything to do with hexagonal cells that form when you boil a liquid from the bottom, and like the Bernard cells?
This I'm not sure. Because there's no other symmetries, when you try to minimize energy, it's not going to do that correctly. So think about it.